Welcome, everyone, and thank you for joining us this afternoon. I'm Andrea, and I will be your host for today's session. I'm glad to welcome today Gregor, who is currently an embedded software engineer at KCF Technologies, where he works on secure boot and embedded platform security. During his master's degree, he researched porting a variety of common side channel attacks to iPhone hardware. And in today's presentation, Gregor will present his work, Apple versus EMA, Electromagnetic Side Channel Attacks on Apple CoreCrypto. Now I would like to invite you to start your presentation.
Sounds good. Thank you, Andrea. Let me share my screen. And okay, so thank you everybody for joining. This is, as you can see from the title, Apple versus EMA, Electromagnetic Side Channel Attacks on Apple CoreCrypto. I'll get started with a little bit of an introduction about myself, although Andrea already gave one. I'm a recent graduate of NC State University, and as part of my master's thesis there, I essentially worked on porting a variety of common side channel attacks to run on iPhones, which is not a very common target for these side channel attacks. As part of this work, I published 2 papers, one called iTimed, which was about digital cache attacks on an Apple chip, and then I also published very recently Apple versus EMA, which is the subject of this talk. Both of these papers were co-authored with Aiden Isu, assistant professor of electrical engineering at North Carolina State University. As part of this work, I've done a decent amount of hardware security research as well as open source work. We released an open source research toolkit for hardware security research on iPhones. I'll talk about a little bit of this in the presentation itself. Currently, as Andrea mentioned, I'm working as an embedded software engineer at KCF Technologies, where I work on secure boot and firmware security. This is a brief outline of kind of the broad topics I'll be covering in this talk. I'll kind of start with some background information about AES, typical side channel attacks on this crypto system, as well as a couple of the statistical techniques that are common. After that, I'll go into the work that we had to do for the attack infrastructure, including what we had to do to physically change the iPhone to make it attackable, as well as kind of the experiment flow, the data pre-processing pipeline, all of these things. Then I'll go into attack development, which is how we actually use the primitives that we built earlier to find vulnerable points in Apple's cipher implementation and talk about a few of the techniques there as well. Finally, I'll talk about the results, analyze how well this attack performs, and point out some conclusions, and then we'll have the Q&A at the end. So let's get started with the background information, kind of the motivation for attacking Apple's crypto libraries in the first place and some of the algorithms and techniques we'll use to do so. As this is a hardware security conference, I'm sure most of you guys are very familiar with AES. It's one of the most popular symmetric crypto systems that's in use today in a variety of applications. And AES is essentially built on these 2 inputs and this output. So for 128-bit or 16-byte plaintext and a key of the same size, what AES does is it entangles these 2 into a ciphertext. And this has some important security properties, mainly if you have the ciphertext but don't know the key, you can't decrypt back to the plaintext. And even if you have both the plaintext and the ciphertext, you still don't learn any information about the key. This is a mathematically very secure algorithm. Over 30 or 40 years of research have gone into breaking it, and we haven't made much progress. But the issue with crypto systems generally is that to take these from a mathematical model to a real implementation, you eventually have to run them on real hardware. And that means that sometimes this crypto system inherits security properties from that hardware. So to that extent, I've kind of broken out the internals of AES in this diagram. To explain this a little bit better, you can see that there's 4 operations: add round keys, subbytes, shift rows, and mixed columns. And we essentially do these over and over again in rounds until we get to the last round, where we replace mixed columns with another add round key. There's also a key expansion phase where the key is transformed into round keys, but this isn't relevant to this research. So if we want to attack AES and actually try to figure out the value of the secret key in a way that the mathematical model says we shouldn't be able to, how do we do this? The most common vector to actually correlate out the secret key for software AES implementations is through cache attacks. And the way that this works is that this subbytes operation here is typically implemented as a lookup table. Essentially, you take the output of add round key, use it as an index into this table, and then take the output of that, and that becomes the new cryptographic state. These tables, though, the subbytes and sometimes these larger T tables, which are sometimes used instead, are accessed at secret dependent indices. So you see we actually combine the key and the plain text, and then this is used to index into this lookup table. So if you can do certain clever things with the CPU's cache, you can actually measure what index we indexed into in this lookup table, and then learn some information about the secret key if you know the plain text. There's a variety of techniques for these. I won't cover them in detail, but you can see, for example, prime plus probe, flush plus reload. There's a whole host of these cache side channel attacks. So the way that this is typically mitigated at the CPU level nowadays is that we actually implement these ciphers fully in hardware, right? If you don't have this lookup table sitting in memory, then you can't do a cache attack on it. If you have circuitry that implements it instead, it never touches the memory, and then those attacks don't work. And for a while now, both x86 and ARM have instruction set extensions that implement AES without these kind of auxiliary memory accesses. Intel has AES-NI, ARM has ARM CE, and these implementations are typically regarded as pretty resistant to these digital cache attacks. But at some level, right, these are still physical circuits inside of the CPU. So the question that I was interested in, and a lot of other people are as well, is are they actually resistant to more analog physical attacks on the hardware itself? In our literature review that we did for this paper, we did find that AES-NI has been shown as vulnerable to power analysis on some Intel chips, but we haven't found any attacks on ARM CE, and hasn't previously been shown to have physical vulnerabilities. So we were interested in this. So if you want to attack hardware, right, we have to define what that actually means and sort of the statistical techniques that we use to do so. The most common technique for this is called correlation power analysis. And this is a technique for determining secret intermediate to the cipher information from physical side channel traces, which is often power consumption or EM radiation, but it can also be weird exotic things like vibration or temperature. All of these are valid vectors for side channels. To do a CPA attack, you need two core pieces of information. The first thing that you need is actually a side channel trace, right? A physical measurement of what you're trying to attack. This is actually a trace from our attack. This shows an implementation of AES running in hardware over time. And for a CPA attack, you need to gather a lot of these. I'll talk about this more in detail later, but we needed about 5 to 30 million of these to run a successful attack. What's also very important is that for each encryption trace, you actually also capture the data that's being operated on. So the specific plain text that's being encrypted, the ciphertext that is the result of that encryption process. And you actually use this associated data to define a so-called leakage model. These are also often called power models, but this word wasn't super applicable to us because ours is actually an EM attack, not power. But essentially what these leakage models do is they return a guess of what the physical activity inside the circuit might be for some given internal state, derived entirely in terms of the plain text or ciphertext, and then also some key guesses. I'll give some more concrete details of how this works later in the talk, so no worries if this doesn't make too much sense at this point. With these physical side channel traces and the leakage models, you can then essentially cross-correlate them together. So this here is the equation for Pearson's correlation coefficient, which is the most typical measure used for this. And what we essentially do is we calculate the covariance between the leakage model and each index of the sample trace. I'll give a more concrete example of this. But then dividing by the standard deviation of both, this essentially normalizes the correlation coefficient into the range from -1 to 1. So it's a more normalized way to kind of look at correlation. Let's give a concrete example of what this actually typically looks like. Let's say we just have one trace, one side channel trace with n samples in it. And then let's say we also define 4 leakage models, right? Which return different guesses of what the internal state might be if the key has a certain value. If we have just one trace, we can't calculate the CPA yet, right? Because these standard deviation terms will be 0 and it's not valid. But let's say we keep collecting more and more of these traces and updating this correlation coefficient. You can see that eventually we get some low correlation values for these specific leakage models and the sample indices. And these don't tell us much yet, right? These are all very close to each other. They don't give us much valuable information. But if we capture even more side channel traces, correlation values will essentially keep going down and down. But at some point, we'll actually see some correlation values which have higher magnitudes than any other ones. By no means high correlation, but higher. You can see, for example, here for leakage model 2 at these sample indices, these correlations are about an order of magnitude higher than all of the other ones. And what this tells us is that there's a good chance that the internal state, which is guessed by this leakage model, is actually observed in the real data, and that it's specifically happening at this point in the time domain. And so we can use CPA attacks like this to identify both what the internal state of some cipher might be, and also where in the time domain this happens. So now that I've kind of gone over some of the preliminaries, we can talk about how we actually apply these to attacking iPhones, which is not a trivial problem in and of itself. As part of this research, we wanted to attack ARM CE, but we actually decided specifically to attack Apple's implementation of this. And there's a couple of reasons for this. First being that pretty much all modern Apple chips are custom ARM cores, right? There's a huge market share out there that's actually these Apple designed CPUs. And yet, not much hardware security research has been done on these Apple SoCs. And this is changing, as platforms are becoming more and more accessible. But even further than that, very few actually focus on Apple's implementations of symmetric ciphers. And we thought this would be a good thing to look at, trust their implementation, but verify. Another reason for this is that we actually already had a pretty good set of capabilities for attacking iPhone 7, which kind of stemmed out of our earlier work with A10. So here on the side, you can see a close view of our acquisition setup. We, of course, have an electromagnetic probe, which was manufactured by Riskier, very good equipment. And then we have our victim iPhone, which has been kind of disassembled here in this figure. You can see that highlighted in orange here, we actually expose the SoC on the logic board itself so that we can probe very closely to what's happening here. We also attach these needle probes to various points on the logic board itself for reasons which I'll talk about in a second. This is a little bit of a higher level view of our experimental infrastructure. We have, of course, the EM probe, which is connected to the oscilloscope to actually measure EM information. But then we've also connected these needle probes into the oscilloscope's triggering input. And what this lets us do is if we can write to one of these test pads on the iPhone logic board with software and set a signal high, then we can actually isolate in the time domain where the encryption might be happening. And it turns out some of these test pads are externally routed GPIO pins, and we were very directly able to set this GPIO pin high, trigger an acquisition, and then find the correct spot in the time domain where encryption is occurring. We also have a power adapter connected to a power supply here because some of these experiments took a while and we didn't want the iPhone's battery to die halfway through, for example. We also have an experiment controller over here, which is a Raspberry Pi, and this kind of coordinates all of this equipment and makes sure things happen in the correct order. So our first attempt at an experiment flow looked roughly like this. Essentially, we use our previously created iTimes toolkit and exploit the iPhone and boot to a full Linux kernel due to some very nice contributions from, I believe, Corellium. There's a fully functioning Linux kernel for iPhone 7 SoCs. We then took Apple's implementation of ARM CE from the CoreCrypto library, which they release under a license for security research purposes, and implement this implementation into Linux's crypto API verbatim without making any code changes. We then connected the needle probes, as I talked about previously, and loaded the iPhone with our experimental program. And this experimental program essentially listens in a loop for incoming plain texts, raises the GPIO pin when it receives one, encrypts whatever the plain text was, and then sends the corresponding ciphertext back to the experiment controller. In this way, we can acquire traces and side channel information for specified plain texts in a coordinated way. And then at the end, we save, of course, these electromagnetic traces along with the plain text and the ciphertext for offline analysis. Now this works, but it has the major disadvantage that this is extremely slow of a setup. And essentially there's a lot of overhead to encrypt any single one plain text to only get one single trace out like this, right? So what we did is we actually modified this somewhat. Instead of listening to incoming plain texts, we actually send random seeds to the iPhone. We then derive plain texts from this random seed and very rapidly and sequentially encrypt these in a row. And we only trigger the oscilloscope once. We collect much longer traces from the oscilloscope like this. On the host side, or on the experiment controller side, we can then use this random seed to derive the same plain texts. We listen to the ciphertext that the device is sending back, and then we have a long trace with much less overhead per encryption with the same associated plain text ciphertext data. These traces look about like this. This is kind of high level. I'll zoom into this here in a bit. But the key idea here is that our oscilloscope had enough sample memory to capture approximately 26,000 encryptions in one trace, which made our acquisition setup about 16,000 times faster than it was before. If we zoom in here, though, a problem quickly becomes clear. Sometimes there's high noise regions which kind of interrupt the encryption process, right? Any encryptions that might happen in this noisy region probably aren't too useful for our CPA attack that we want to define. So we need to do some kind of pre-processing to pick out the correct traces that'll actually be useful for us. If we zoom in even further here, you can see individual encryptions. Each of these spikes is one encryption on a 128-bit block. And the key problem here is that we actually need to take each of these individual encryptions and spikes and figure out exactly which seed-derived plaintext was the input to this encryption. Because remember, CPA is very sensitive to having this trace and associated data combination. And if we don't have this, or if it's wrong, it actually negatively affects the CPA attack by introducing noise and potentially leading to a failed attack. So what we came up with is an approach to kind of split these, we call them subtraces, out of the bigger trace. And we originally tried to use pattern matching for this, right? If you look at these spikes, they all have kind of a predictable pattern, and we can use pattern matching to try to say at these points in the time domain is when encryptions happen. But if there's noise, this doesn't work, right? Then we don't have good pattern matches anymore. In all of these regions, for example, we don't see this. And even if we don't know where these noisy traces are in the time domain, we still need to know how many of them we missed, so we can find the correct plaintext after the noisy region that's the crypto system is operating on. So what we did is we also used timing measurements at the start of each encryption block. Our experimental program saves a timestamp of when the encryption occurs. We can actually use this to then count how many plaintexts we miss in these high noise regions. So in this graph over here, you can see traces in red where we have the timing measurement only, where the pattern match failed due to noise. And in the green traces, these are actually traces where we have the timing measurement as well as a reliable pattern match. And you can see in the high noise regions, we only have the timing measurements to tell us how many we missed. And you can see even some regions like right here, where there's no encryptions happening at all. So some kind of interrupt happened here to interrupt our experimental program. So now that we have these primitives, we have the ability to quickly gather long traces and split them apart into useful traces for a CPA attack. We need to figure out enough about the implementation to actually attack it. And to do so, we first started with a known key analysis. What a known key analysis essentially lets us do is it lets us reverse engineer the underlying hardware through the idea of kind of making some guesses at how things might be implemented. And from an implementation perspective, we don't know much about what the underlying hardware is doing. We know it's AES, we know it uses these instructions, and we know those instructions execute in the floating point pipeline. But now we need to find these good leakage models that will actually let us correlate out secret information. If we pretend that we know the secret key, at an algorithm level, we can derive each intermediate state of each operation. And we can then define leakage models that correlate with those EM traces and tell us, is this intermediate state of the cipher even visible in the data? Because if not, then we shouldn't even try to attack this. I'll give a concrete example of how this works on the next slide. But the key idea is that any leakage model that stands out in this known key attack could also work for an unknown key attack where we try to correlate that out. So here's kind of an overview of how this known key analysis works. We derive these known key leakage models and correlate with them. At this point, we assume we know all of this intermediate information and we can directly calculate all of its intermediate state. We start with just a leakage model for the plain text, right? Given any plain text byte, we can calculate its Hamming weight, which is the number of bits that are set, and then correlate this with the trace in a straightforward way. We can then proceed, since we know the key, we can add it and then get the output of the add round key operation. We can then substitute the bytes, shift the rows, kind of proceed step by step algorithmically through this crypto system. And we know each intermediate state, so we can correlate with it. Eventually, we finish round 0, do some more rounds and get to round 8. We proceed through the last steps here. And then we take the branch to the last add round key instead. And now we can also look at the ciphertext. In total, we have 656 of these known key leakage models, 16 byte positions, and then 4 operations per round times 10 rounds. And we also include the plain text state. So we have 656 power models that we're correlating with each trace. And we're trying to see which internal state is visible in the data. When we look at our results here, we may have some correlation plots that show time on the x-axis and absolute correlation magnitude on the y-axis. And you can see that for many of these operations, there's actually no activity or correlation visible, even if we know the secret key, even if we know exactly what the intermediate state is. But a big exception to this is actually the output of the mixed columns operation. For the output of this operation, we see strong correlation plots at each of the rounds. And we actually see that the peaks of these correlations advance further in the time domain as the round increases. So we can see the output of any mixed columns in the cipher. This is obviously a good hook, potentially into an attack, right? If we can somehow calculate the output of a mixed columns operation from only the plain text or ciphertext and some key guesses, then we might be able to find support for certain key guesses and figure out which might be correct and which might not be. And that's exactly what we do. So next we have to define these specific leakage models. We know the output of mixed columns is leaky, so how can we get to the output of mixed columns from only the plain text or the ciphertext? The first option that we have available is attacking the first round's mixed columns, right? If we go back to our known key attack, this happens right here. And the core issue with this is that in order to guess the output of 1 byte of this intermediate first round mixed column state, we actually need to make guesses at 4 bytes of the key, because these are combined in this specific way with the plain text, which means that in order to fully explore all of the potential leakage models, we would need to define 2 to the 32 of them, which is a large number. And this is most likely a computationally infeasible approach, because in order to guess any single internal byte and correlate to it, we need to actually guess 4 bytes of key. The second option that we have is to actually look at the last round's mixed columns operation, right? If I go back to the known key analysis, we see this right here. And the key idea here is, in order to get back to this, we only need to invert this add round key, shift rows, sub bytes, and another add round key, and then we're back to the output of a mixed columns. We don't actually need to pass through a mixed columns. And what this actually turns out is that for this power model, we only need to guess 2 bytes for the key rather than 4, which is 2 to the 16 power models. And this is much more than 2 times speed up. This is a square root speed up even. This is a much more efficient attack if we actually try to correlate out the last mixed columns. And this means that our final power model looks like this. We essentially guess 2 bytes of key. We invert it into a specific internal state that we suspect might be due to that key. And we need to do so for each possible combination of these values. So now that we have these results or these leakage models, how does our attack actually perform? Our attack process looks approximately like this. We acquire a large amount of side channel subtraces using the sort of denoising post-processing approach that I described earlier. And then for each of these traces, we use the associated data and all 65,000 key guesses to calculate the values of the leakage models for that trace. We then cross-correlate those leakage model values with each sample index of data, which is computationally expensive, to say the least, and we update our running Pearson correlation values. And then what we can also do is optionally, every n traces that we aggregate in this way, we can save this intermediate correlation state, and this kind of helps for the visualization purposes. once we've aggregated a high enough number of traces, calculated correlation to a high enough degree, what we can do is we can take the correlation values for each leakage model across the time domain and find the maximum value in that time domain, and then actually sort by that, right? And the thinking here being, if a leakage model has a high correlation value, this might be evidence that those key guesses associated to that model are correct, and then that we actually see leakage at that point in time. If we then also know the key, we can take the log of the correct guesses sorted index as about a measurement of how hard it would be to break that byte position. I'll give an example of this in a bit here too. So here's some of the results actually that we see. These plots first show correlation magnitude versus the time domain. Blue lines are the correct key guess. Red lines are the inverse guess, which I'll talk about in a second. And all of the gray lines are the wrong leakage models. And you can see after aggregating enough traces, it's actually very clear the correct model stands out from any of the other ones. If we instead look at how this correlation coefficient evolves as the number of subtraces that we've aggregated increases, you can see that starting at about 10 million traces for this byte position even, the correct model is very clearly discernible from all of the incorrect models. So this is actually our attack working. This is our attack pulling out the key from this electromagnetic radiation just through correlation with our leakage models and attacking the output of the mixed columns operation. About this inverse guess, we found that this actually has a similarly high correlation magnitude. It also stands out from any of the other traces. And this actually corresponds to the specific model where the last key guess is correct, but the second to last key guess is the bitwise not of the correct one. So it's actually very tightly related to what the correct key guess is. If we now take these results and break it down per byte position and actually try to see how easy it is for us to break a certain byte of the key, you can see that on average, it takes between 5 to 30 million traces only to actually correlate out what the secret key at that position is. These plots show the number of subtraces that we've aggregated versus this security level measurement that I talked about earlier. We would take the log of this correct guesses sorted index. And you can see this initially starts at about 16, which makes sense because we have to guess 2 bytes of key for every 1 byte to actually correlate with. But quickly, this actually goes below 8 bytes. So it's just as good as a brute force on AES. And then in pretty much every case, actually, the correct key model becomes the first one in the sorted list. So it has the highest correlation magnitude, so we can discern it from all of the other ones. At some of these byte positions, you can even see the effects from the inverse guess, which is a very similar absolute magnitude. So it quickly flips back and forth between the correct guess and the inverse guess. So in conclusion, what we wanted to do was break ARM CE and try to show that these implementations might still have physical vulnerabilities, even if they're digitally secure. We were able to use standard EM acquisition from acquisition equipment from Riskier, an existing open source toolkit and some optimized analysis code. And we were actually able to break Apple's hardware implementation of AES. With about 5 to 30 million subtraces per key position, this is actually enough to correlate out the secret key. And if we do some quick math, this actually is not that high of a requirement. With 128-bit blocks, that means we must only observe encryption on about 80 to 480 megabytes of data. And at 62.5 nanoseconds per encryption, you could theoretically acquire all of the data that you need to break the AES key in less than 2 seconds with enough advanced acquisition equipment, with enough sample memory. And our argument in our paper is actually that these requirements fit realistic mobile application behaviors. Think maybe in terms of cloud backup solutions, right? These are files that are zipped together, encrypted, and then sent out over the network. If the attacker controls the network, they can observe the ciphertexts. And if they can also find some way to gather EM traces from the encryption process of the backup, then they can decrypt all of your files as they get sent out over the network. This is also applicable to software updates, decryption for reverse engineering purposes, and others. But kind of the main point that we wanted to make with this work is a lot of these side channel attacks are done in laboratory settings, right? And actually, they're not always applicable to the real world, either in terms of computational complexity or the amount of time needed to acquire traces. So what we believe is that there's actually more work needed to determine what the real life threat is from these side channel attacks. And that was the goal kind of with attacking an iPhone, very ubiquitous device. A lot of people know it. And the fact that we succeeded should show that we need to do some things different. With that, that's my talk, and I'd be open to take any questions if anybody has them.
Thank you very much for the presentation. I would like to invite everyone to share your questions in the chat box if you have any. Let's wait a little bit.
Sounds good.
There is a question already. Did you try other leakage models except Hamming-Weight?
We did not, although we did kind of speculate on some ways that this might look. The other common leakage model is Hamming distance, right? Which kind of measures the activity that might occur due to some state registers changing state. And the main issue there was that these instructions actually execute in the floating point pipeline. So if we could calculate the Hamming distance between one register state and another after executing one of these ARM CE instructions, then we could potentially break the key. But this is an advanced processor. It has out of order execution. It has, a bunch of physical registers backing the logical registers. So we actually had no way to ensure that the output of some ARM CE instruction would go back to the same physical register as before. Of course, we could then spray register values into the physical registers and try to correlate that way, but it seemed a little bit more complicated to try to do this than the Hamming-Weight-based attack that we ended up doing.
Thank you for answering this question. In the meanwhile, some people said thank you, and that is a great presentation, but we also got two other questions. One is, would you expect other ARM processors implementing ARM CE to be vulnerable as well? In other words, does the ARM CE on Apple cores differ from other ARM cores?
Yeah, that's a great question. Knowing Apple and their sort of corporate philosophy, I am sure they did something weird for their specific ARM CE implementation. And we can't really claim also that other ARM CE implementations would be vulnerable. But kind of from an architectural standpoint, right? The way these instructions are implemented, how this works, it almost shows that there could be a vulnerability. Of course, somebody needs to do a concrete attack, although the, I guess, generic execution model and how instructions are executed in these processors would be similar. So I would expect that there might be leakage, but someone needs to double check.
Thank you. Another question is, any ideas why the mixed columns instruction is more leaky than the other one?
I have some guesses. If we look specifically, where is it? What the mixed columns instruction actually involves, right? It's a lot of multiplications and then it's a lot of additions. So I imagine in the background, actually, this is a very arithmetically intense operation, and the output of that seems to leak in some way. So I imagine that mixed columns just, it's more than just a simple exclusive OR. It's more than just a table lookup or just changing indices. It's actually a lot of adding and multiplying. So my guess is the higher activity from that makes it more visible for a side channel attack and more exploitable.
All right, thank you. Are there any more questions? I don't see any. Oh, we do have. How many samples are in a single encryption trace at the frequency you are recording the trace? What sampling frequency are you using for the traces?
Yeah, great question. So in a trace that looks approximately like this, one of these subtraces, this is about 10,000 samples. For these bigger traces, like I show here, this is 32 million traces acquired at a 10 gigahertz sampling rate with a 1 gigahertz bandwidth on the oscilloscope.
Thank you. Thank you. All right, I think that we don't have any other questions. I would like, oh, there is another one. My understanding is that side channel attack typically requires sophisticated lab setup to execute. Can side channel attack happen outside the lab?
This specific one, probably not as easily, no, because it does require this close physical access and this kind of bigger acquisition setup. There are other kinds of side channel attacks that are much more easy to do outside of a lab setting. For example, cache attacks, right? That's software attacking software across boundaries or across privilege boundaries, which means you don't necessarily have the same lab requirement. There's also a couple of really fascinating attacks that use SoC internal power monitoring systems to actually do remote physical attacks. So this paper that I referred to, which attacked AES and I, these actually use an Intel power monitoring interface, which they can have software monitor, and they can run a physical side channel attack through that. So this attack probably cannot succeed outside of a lab, but others definitely can and have.
Thank you. And I think we got another question in the meanwhile. Interesting topic with many questions. In the correlation traces, correct and inverse, the highlighted region, is it the time when encryption is taking place, hence the leak is seen, or is there any reason for only that time region being the leaky temporal region?
So this specific leaky region in the time domain would correspond to about when the last mixed columns operation is happening. Sorry, wait, let me look at the question again. Yes, so this is the time when the specific sub-operation of the encryption process is taking place. And as you can see in this known key plot, actually the specific time location can vary as well, depending on if you're targeting the first mixed columns or the last one. So yes, yeah, the leakage model essentially returns the time when the specified operation is taking place.
Thank you very much. No more questions. People saying good work and thank you. I would also like to thank you for coming and doing this presentation for us. And I think that we can conclude with the webinar. Thank you once again.
Sounds good. Thank you for having me, Andrea.
Have a nice day, everyone. Bye-bye.